Okay, last video was stopped here, right? Scale and inference. I mentioned that scale is a tricky thing, and when you are transferring information across scales, there could be different types of inferential error. There are three types of them: individualistic fallacy, ecological fallacy, and a cross-level fallacy. In this video, I'm going to provide more examples and explain what these fallacies are. First one, individualistic fallacy, also known as reductionist fallacy, using micro-level data to make macro-level inferences. Okay, I'm going to use this small, say, comic to explain this. Okay, on the left side, this comic is kind of sexism. Okay, on the left side, we have an instructor on the left, a student on the right is a boy, and this boy is not good at statistics or mathematics. Okay, say mathematics. The instructor said that, whoa, you suck at math. Okay, it's fine, it's all right. But on the right, here is a girl. She's not good at math either. But this time, the instructor said that, whoa, girls suck at math. So do you see the mistake here besides the sexism? So this girl is pretty good, is pretty bad at math. That is okay. You can say, okay, you are not very good at math. Or you can say, you suck at math. But you cannot say that since this girl is not good at math, then girls all suck at math. This is a key error here. You cannot draw conclusions on individuals and just simply move this conclusion for the whole group, for the whole population. This is a very typical individualistic fallacy. It means that when you are drawing a conclusion from a phenomenon happening at a lower scale, you simply cannot move this conclusion for another research, for another phenomenon at a higher level. Okay. This is the first type of fallacy. Second, ecological fallacy, using micro-level data to make micro-level inferences. It is an opposite. It is the opposite of individualistic fallacy. It means that when you have drawn some conclusion based on the data for the whole group, you should not simply use this conclusion for an individual in this group. For example, here we have a group of people, 1, 2, 3, 4, 5. 5 people with different, say, yearly income. 210K, 80K, 12K, 40K, and the richest one has 1 million. So there is a huge difference between their annual income, and the average value of their annual income is $175,800. This is the average value, which means this conclusion is based on this whole group. But can you say that each individual in this group should have a yearly income of this specific value? No, you can't, because some of the people here in the group, they have higher annual salary than this. Some of them lower. Okay, so the mistake is here is that assuming that individuals of a group have the average characteristics of the group, and confusion between group correlations and individual correlations. In summary, we have examined the first type of fallacy, right? We have examined the second type of fallacy. In summary, if you draw conclusion at a specific scale, this conclusion stays at that scale. Do not use it for a a higher level scale phenomenon or a lower level scale phenomenon. Okay, so do not, when you draw conclusion, it stays here. It stays at that level, stays at that scale. Okay, and there is another very famous say example for ecological fallacy is called Simpsons Paradox. Trend appears in different groups of data, but disappears or even reverses when these groups are combined. Here is an example. Here we have a scatter plot with blue dots and the red dots. Okay, and this scatter plot is between temperature in Celsius degree and latitude. Okay. Okay, so obviously there are two groups, right? Group 1, region 1, group 2, region 2. And each dot here is representing a temperature measurement at a specific location in that specific region. So let's just ignore region 2 first. Let's focus on region 1. So we have multiple measurements from multiple locations with different latitudes, right? And for each location at a specific latitude, there is a measurement for temperature. So if we ignore the red part, let's focus on the blue part. What's the correlation between latitude and temperature? Is it positive or negative? Obviously, it is negative, because as the latitude increases from 20 to 30 to 40, there is a general trend that the temperature drops, right? So all those locations with latitudes around 20 degree, they have higher temperature. On the other hand, all those locations with latitudes around 40 degree, they have relatively lower temperature readings than those with lower latitudes. So it's negative correlated for region 1. Okay, latitude and temperature, they are negatively correlated. If we ignore the first region or the region, the blue region, region 1, let's focus on region 2. It's the same correlation here, right? From 40 degree to 60 degree, as the latitude increases, the temperature readings also drops. They also drop for region 2, for those red dots. So for these two regions, if you separate them, you look at either one of them, the correlation is negative, which means that the higher the latitude, the lower the temperature. But if you put them together, let's consider both of them. Let's consider all these red dots and blue dots together. In this large scatter plot, what's the correlation between latitude and temperature? Although this correlation is pretty weak, but we can simply use this dashed line to represent the correlation between latitude and longitude. It means that the higher the latitude, the higher the temperature, right? Although all those blue dots, they are representing locations with lower latitude, they have what? They have relatively lower temperature compared to region 2. Region 2 has what? Has a relatively higher latitude, but they also have relatively higher temperature readings compared to region 1. So although this relationship is pretty weak, because you can see that these blue dots and red dots, they are not distributed along this line. But in general, what I said is the fact: the higher the latitude, the higher the temperature. So when we're talking about region 1 and 2 separately, this correlation between latitude and temperature is negative. Now it's positive. This is a very good example for Simpsons paradox. Okay, results from different groups of data disappears or even reverses when groups are combined. Group 1, group 2, for either of them, correlation was negative. But if you combine them, put all of the dots in this scatter plot, the correlation reversed. is now positive. Okay, so you should be very careful with scale. Okay, when you're addressing GIS or spatial or related um, issues, problems. Okay, and there is another famous paper on ecological fallacy, ecological correlations and the behavior of individuals. So this paper discussed the illiteracy rate and foreign-born in 1930 census. There is a very famous conflict here. Okay, the state-level result of the census shows that the greater the proportion of immigrants in a state, the lower its average illiteracy, which means that if a state has a lot of immigrants, then the illiteracy of the state is low, which means that maybe these immigrants, they are all educated or they are more educated than local people. That is the conclusion you can draw from state level data, state level result. But at individual level, the result is totally different. The result indicates that immigrants were on average more illiterate than native citizens. So it's completely opposite to the conclusion you can draw from state level. So there could be a lot of reasons, but there is maybe I would say this is the most reliable reason for this conflict. Negative correlation at the state level, because immigrants tended to settle in states where the native population was more literate, so that the business is pretty would be better in those states with educated people. So immigrants, they had higher possibility to find a job. So I would say at individual level, this result is reliable, which means that in fact immigrants, they were less educated, but they want to go to states with educated people. That's the reason why at state level you have a totally different, totally opposite result here. Okay, I think this example is just clear enough. Is clear enough for ecological fallacy. Okay, you can draw totally different conclusions at individual level and at higher levels. Okay, and the third type of fallacy is called cross-level fallacy. Fallacy. This is relatively easy to understand. It means that using data from one subpopulation to make inferences about another subpopulation. For example, you can draw conclusion about the relationship between the proportion of educated people and the local GDP. Okay, you can do this in Ohio, but the conclusion should stay at Ohio. You cannot use this conclusion in Louisiana, in Illinois, or in Wisconsin. Okay, even there is no change of scale here, right? All I mentioned were states. They're at same level, right? State level research was done at state level for Ohio, but you cannot use this result, this conclusion, to apply to other states. And since we're talking about scale dependency, there is something I would like to introduce. It has nothing to do. It's not a specific. It doesn't belong to one of the three types of fallacies here, but I would say it contains all of them. This problem is called Modifiable Aerial Unit Problem, MAUP. Remember this term, okay? It's pretty important in GIS, not only in simulation and modeling. So the idea is that if the spatial units are arbitrary, which means they are modifiable, the results of analysis based on those units are also arbitrary, which means modifiable. It means that in summary, it means that if you draw a conclusion at a scale, it stays there. And if you have drawn some conclusion based on a specific zoning method, that conclusion stays with that specific zoning method. If you change the zoning method to rezone the same area, to divide the same area into small units using different methods, your conclusion should not be applied. So here is an example. So for example, here we have 9 enumeration units, and this grid is showing the population for each unit. Okay, unit 1, 100 people, unit 2, 100 people, etc., etc. Okay, and here on the right side, we have unemployed count for each enumeration unit. So 10 people out of 100 in unit 1 do not have a job. 20 people out of 100 in unit 2 do not have a job. Okay, so if you divide 10 by 100, you have 10% as the unemployment rate for enumeration 1, right? So it's a very simple calculation for unemployment rate. So here is the result. But this result, this conclusion stays for this zoning method, for this design of enumeration units. Because if you redesign the zoning method, for example, now we don't have 9 enumeration units within this area, we have 3 of them. Then you can see that the unemployment rate becomes more stable. For unit 1 is 7%, unit 2 8%, unit 3 9%. Is 9%. So compared to the original one, the unemployment rate varied from 3 to what? To 25%. Here is more stable. Okay, you have a better looking data to show. And this is a scale issue because obviously the new units, they're larger than the original units. And here we use different zoning methods, okay, from 9 units to 3 units, enumeration units. And now even we use the same zoning method to divide the whole area into 3 units, okay, 7, 8, 9. But if we use another method to do the same zoning, 15, 7, 8, 16, 5, 6. So this is a game of what? Of planning, of zoning, okay? So according to your specific method, at a specific scale, at different scale, or even at the same scale with different zoning methods, you could have totally different conclusions, okay? So this is MAUP. And this is the end of the first lecture of chapter 2. I will see you in the second lecture of this chapter. Thank you.